Welcome to AI Frontiers, where today we're exploring recent advances in computer science game theory. This field represents a fascinating intersection where mathematical models meet practical applications, influencing everything from voting mechanisms to resource allocation and blockchain economics. In this episode, we'll synthesize cutting-edge research that's shaping how we understand strategic interactions in computational systems. Join us as we dive into this rich landscape of strategic decision-making and explore what recent research reveals about the future of this field. We'll examine the theoretical foundations, practical applications, and emerging trends that are defining this rapidly evolving discipline at the crossroads of game theory and computer science. Computer science game theory sits at the intersection of economics, mathematics, and computer science, applying mathematical models to understand strategic interactions among rational decision-makers. This field has become increasingly significant in the design and analysis of algorithms, mechanisms, and systems where multiple participants interact, each pursuing their own objectives. Unlike traditional game theory from economics, computer science game theory explicitly considers computational constraints, addressing questions about the complexity of finding equilibria, designing computationally efficient mechanisms, and analyzing how bounded rationality affects strategic outcomes. The field provides theoretical foundations for designing fair voting systems, efficient resource allocation mechanisms, stable matching algorithms, and analyzing strategic behavior in networks and multi-agent systems. Its significance continues to grow as our world becomes increasingly interconnected and automated, making it essential to understand how autonomous agents interact, compete, and cooperate for designing fair and efficient systems. The first major research theme in computer science game theory focuses on electoral systems and voting mechanisms. Recent papers in this area examine how different voting rules affect outcomes and how to design systems that satisfy desirable properties like proportionality and fairness. Several researchers have investigated proportionality in ordinal elections, specifically examining systems like the single transferable vote using real-world election data to determine how well theoretical proportionality axioms translate to practical scenarios. Other scholars have introduced concepts like a proportional veto principle for approval ballots, exploring how large groups of voters can effectively veto candidates they disapprove of. Some researchers have taken a more mathematical approach, using analytic combinatorics to calculate the probability of a Condorcet winner, a candidate preferred by a majority when compared head-to-head with any other candidate, in large electorates. This research is particularly relevant as societies grapple with designing electoral systems that better represent voter preferences and produce outcomes perceived as legitimate. Studies on ballot truncation, where voters rank only some candidates rather than all, provide practical insights into how incomplete preference information affects proportionality. The second prominent research theme concerns fair resource allocation, with particular attention to equity and envy-freeness in distribution problems. Researchers are studying facility location problems where one facility must be built at a location chosen from a set of candidates, with agents having private positions and preferences. Their work explores how to design mechanisms that incentivize truthful reporting while approximating optimal social welfare. Other scholars are revisiting the concept of weighted envy-freeness in resource allocation, proposing new concepts that increase the likelihood of finding fair allocations across different contexts. A significant body of work investigates best of both worlds guarantees for equitable allocations, aiming to achieve both expected equitability and ex post approximate equitability in randomized allocations of indivisible items. These approaches develop algorithmic solutions to fairness challenges in various resource distribution contexts, from inheritance division to task allocation in teams. This theme reflects growing interest in fairness considerations in algorithmic decision-making, particularly as algorithms increasingly determine the allocation of scarce resources in various domains from healthcare to housing. Strategic information sharing in competitive environments forms the third major research theme. Several papers model how information is strategically shared, sold, or manipulated when agents compete. For instance, some researchers model a competitive market as a game of incomplete information where one player observes some payoff-relevant state and can sell messages about this state to competitors. They frame this as a product versioning problem and derive insights about when and how information should be shared amongst competing firms. This work addresses fundamental questions about the strategic value of information and optimal disclosure policies in competitive settings. Other research explores incentive-aware machine learning, focusing on algorithmic decision-making in contexts where individuals can strategically modify their inputs to influence outcomes. This emerging field bridges the gap between machine learning and strategic behavior, addressing a growing challenge as algorithmic systems become more prevalent in high-stakes decision contexts. These papers develop frameworks for balancing information revelation with competitive advantage, recognizing that strategic agents will adapt their behavior based on how information is used in decision-making processes. The fourth and fifth research themes encompass multi-agent systems and blockchain economics. Researchers investigate the dynamics of coordinating and anti-coordinating agents in co-evolutionary models for actions and opinions. Their work examines how individuals in a population interact on multi-layer networks, sharing opinions and observing others' actions while revising their own according to game-theoretic mechanisms. Other scholars propose novel deep reinforcement learning frameworks to model agent strategy optimization in spatial public goods games, addressing cooperation evolution mechanisms in dynamic environments. In the blockchain domain, researchers study pool formation in proof-of-stake protocols, where stakeholders can form pools to obtain regular rewards from participation and ledger maintenance. They analyze mechanisms for splitting rewards among pool members, comparing the Shapley value scheme from cooperative game theory with standard proportional schemes. Game-theoretic models for airdrop games examine how newly minted tokens should be allocated to pre-existing sets of potentially interested parties to encourage participation in new blockchain systems. These themes reflect the growing importance of understanding strategic behavior in networked environments and designing effective incentive mechanisms for decentralized systems. Several groundbreaking findings have emerged from recent research in computer science game theory. One significant result concerns logarithmic memory bounds for near-optimal play in stochastic games. Researchers have proven that in any stochastic game, for any epsilon greater than 0, there exist uniform epsilon optimal memory-based strategies that use at most O, log n, memory states in the first n stages, a substantial improvement over the previous O, n, bound established in 1981. This dramatically reduces the memory requirements for implementing near-optimal strategies, making them more practical for real-world applications. Another key finding challenges conventional wisdom about proportional representation in elections by showing that solid coalitions of the required size, which are theoretically necessary for proportionality axioms, rarely occur in practice. This suggests theoretical proportionality guarantees may not translate effectively to real-world scenarios. A third significant finding relates to best of both worlds guarantees for equitable allocations, proving that such allocations always exist for two agents but may not exist for three or more agents. Additionally, researchers have introduced a unified framework for incentive-aware machine learning that encapsulates three distinct perspectives: robustness, fairness, and causality. Finally, novel dynamic Bayesian persuasion pricing mechanisms for online federated learning have demonstrated improvements in accuracy and convergence speed by approximately 17%. Recent computer science game theory research employs several distinct methodological approaches. Axiomatic analysis defines desirable properties that mechanisms should satisfy and then analyzes which mechanisms meet these criteria. This provides a clear, normative framework for evaluation but may not capture all relevant considerations or real-world constraints. Game-theoretic equilibrium analysis identifies stable states where no agent has an incentive to unilaterally deviate, offering predictions about rational agent behavior but potentially overlooking bounded rationality or computational challenges in finding equilibria. Algorithmic mechanism design combines algorithm design with game-theoretic incentive analysis to create mechanisms that achieve desired outcomes when participants act strategically, bridging theory with implementable algorithms but often requiring trade-offs between incentive compatibility, computational efficiency, and other properties. Empirical analysis and simulation evaluate theoretical predictions using real-world data or controlled experiments, grounding theory in practice but potentially limited by data availability or modeling assumptions. Finally, computational complexity analysis establishes fundamental limits on what can be efficiently computed, guiding algorithm design but sometimes yielding overly pessimistic worst-case results that don't reflect typical instances encountered in practice. The paper, Stochastic Games with Limited Public Memory, by Hansen and colleagues represents a significant breakthrough in understanding memory requirements for optimal play in stochastic games. The researchers established that in any stochastic game, there exist uniform epsilon optimal memory-based strategies that use at most O, log n, memory states in the first n stages. This represents a substantial improvement over the previous O, n, bound established by Mertens and Neyman in 1981, dramatically reducing the memory requirements for implementing near-optimal strategies. The authors also proved the existence of uniform epsilon optimal memory-based strategies whose memory updating and action selection are time-independent, such that with high probability, the number of memory states used up to stage n is at most O, log n. Importantly, they demonstrated that this result cannot be extended to strategies with bounded public memory, illustrating this impossibility through the big match game. This limitation highlights a fundamental boundary in the design of memory-efficient strategies for stochastic games. The findings have significant implications for implementing game-theoretic solutions in resource-constrained environments, from mobile devices to embedded systems, making optimal strategies more practical for real-world applications. The research on quantifying proportionality in elections has yielded important insights into the gap between theoretical voting system guarantees and real-world outcomes. Researchers have developed quantitative measures of proportionality in voting systems and applied these metrics to real-world election data, challenging conventional wisdom about proportional representation in ordinal elections. Their work shows that solid coalitions of the required size, which are theoretically necessary for proportionality axioms, rarely occur in practice, suggesting that theoretical proportionality guarantees may not translate effectively to real-world scenarios. By comparing different voting rules including single transferable vote, single non-transferable vote, the expanding approvals rule, and sequential ranked choice voting, the researchers provide empirical insights into which systems actually deliver proportional outcomes in practice rather than just in theory. Additionally, their study of the effects of ballot truncation, where voters rank only some candidates rather than all, offers practical insights into how incomplete preference information affects proportionality outcomes. This research bridges the gap between theoretical voting system analysis and empirical electoral outcomes, providing valuable guidance for designing more effective and representative voting systems. The research on dynamic Bayesian persuasion for online federated learning addresses a fundamental challenge in distributed machine learning: how to incentivize clients to participate in training when both the server and clients have incomplete information about each other's resources. The researchers introduced novel dynamic Bayesian persuasion pricing mechanisms for online federated learning under two-sided incomplete information, formulating the interaction between the server and clients as a dynamic signaling and pricing allocation problem within a Bayesian persuasion game. They demonstrated the existence of a unique Bayesian persuasion-Nash equilibrium in this context. Experimental results showed that their approach optimizes accuracy and convergence speed by 16.99% and improves the server's utility by up to 12.6% compared to baseline approaches. This work represents a significant step forward in the design of incentive mechanisms for federated learning, particularly in dynamic online settings where clients arrive sequentially. The integration of Bayesian persuasion techniques with federated learning provides a novel approach to addressing incentive issues in distributed machine learning, with potential applications in privacy-preserving AI systems where data remains local while contributing to global model improvement. Looking ahead, several promising future research directions emerge in computer science game theory. First, bridging theoretical guarantees with empirical outcomes in voting system design remains a critical challenge, requiring more real-world testing of theoretical voting mechanisms and the development of metrics that better capture practical considerations. Second, developing computationally efficient algorithms for fair resource allocation, particularly for settings with 3 or more agents where, best of both worlds, guarantees may not exist, presents an important avenue for exploration. Third, expanding incentive-aware machine learning frameworks to address increasingly sophisticated strategic manipulation tactics will be essential as algorithmic decision systems become more prevalent. Fourth, creating comprehensive game-theoretic frameworks for decentralized systems beyond blockchain, including decentralized autonomous organizations, peer-to-peer networks, and multi-agent AI systems, will help design robust incentive mechanisms for these emerging technologies. Finally, exploring bounded rationality models that better reflect actual human strategic behavior, rather than assuming perfect rationality, will lead to more realistic predictions and more effective mechanism designs. These directions highlight the field's continued evolution at the intersection of theoretical computer science, economics, and practical system design. This presentation was synthesized using AI tools including GPT and Claude 3 Sonnet. Text-to-speech synthesis was performed using DeepGram technology, while visual elements were generated using OpenAI image generation capabilities. The content underwent review by a human expert to ensure accuracy and coherence. While comprehensive, some oversights may exist despite careful review of all references. The presentation represents a synthesis of current research in computer science game theory, drawing from multiple papers published on the arXiv preprint server and in peer-reviewed journals. The goal was to provide an accessible overview of recent advances in this rapidly evolving field while maintaining technical accuracy and highlighting the most significant contributions. Future episodes will continue to explore emerging research across the spectrum of computer science and artificial intelligence, providing similar syntheses of complex technical domains. Subscribe to AI Frontiers to stay updated on the latest research in computer science and AI. We provide regular synthesis of cutting-edge papers across emerging fields with accessible explanations of complex technical concepts. Join our community of researchers, practitioners, and enthusiasts by subscribing to our YouTube channel for more research presentations. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.